If your answer is 3.876 and you write 3.88, it looks correct. But in physics, that small change can make your final answer wrong. Not because of physics, but because of precision. Today, I will show you how rounding and significant figures decide whether your final answer is significantly meaningful or misleading. Hello everyone, welcome back to evigyan. In this series, we have already discussed units, dimensions, and dimensional analysis. Today, we take the next crucial step that connects measurement, numbers, and scientific honesty. Today's topic is rounding of numbers and significant figures. Why precision matters in physics? In physics, measurements are never perfectly exact. Every measuring instrument has a limitation. So when we write too many digits, we often create a false sense of accuracy. That is why physics uses two powerful ideas, rounding off and significant figures. Together, they help us to present results clearly and match calculations with measurement precision. What is rounding off? Rounding off is the process of approximating a number to a required level of precision. Instead of writing long decimal expansions, we replace them with values that are simpler and more meaningful. To round a number, identify the digit you want to keep. Look at the digit immediately to its right. If it is 5 or greater, round up. If it is less than 5, keep the digit unchanged. Remove all digits after that. Let's take an example. Round 5.776 to 2 decimal places. Here the third decimal digit is 6. Since 6 is greater than 5, we round up. So final answer will be 5.78. Take the second example. Round 3.123 to 2 decimal places. Here the third decimal digit is 3. Since it is less than 5, we keep the digit unchanged. We are not going to round up. And the final answer will be 3.12. But there is a special case here. What we will do when the digit is exactly 5. In scientific data analysis, to reduce bias, if the digit before 5 is even, keep it unchanged. If it is odd, round up. For example, 2.5 becomes 2 and 3.5 becomes 4. Why 2.5 becomes 2? Because 2 is here even number. So we are going to keep it unchanged. And in 3.5, 3 is odd number. So we have to round up. Now let's discuss about the rounding errors. It is very important for examination purpose. Repeated rounding during calculations can introduce accumulated errors. That's why in physics, we do not round intermediate steps. We round only the final result. Now let's understand what are the significant figures. Significant figures tell us how precise a measurement really is. They are the meaningful digits, the digits that carry real information about a measurement. In physics, significant figures communicate certainty, reliability, and experimental limitations. Every measurement has uncertainty. No instrument is perfect. Significant figures help us to avoid false precision, report result honestly, and respect experimental limitations. So now let's discuss about the rules of counting significant figures. There are many rules. The first rule is non-zero digits. All digits from 1 to 9 are always significant. For example, 123.45 has 5 significant figures because here all digits are non-zero. Now let's move to the second rule, that is leading zeros. Zeros before the first non-zero digits are leading zeros and they are not significant. For example, 0.00456. Here 4, 5, 6 are significant. So we have how many significant figures here? 3. These zeros only indicates decimal positions and they are not going to count as a significant figure. The third rule is captive zero. What are captive zeros? Captive zeros are those zeros which are between two non-zero digits. So zeros between two non-zero digits are always significant. For example, 10.05. How many significant figures here? 4. The fourth rule is trailing zeros. What are trailing zeros? Trailing zeros are those zeros which are after non-zero digits. So trailing zeros are significant only if a decimal point is present. In 100, how many significant figures? One significant figure, because there is no decimal point here. So trailing zeros are not significant. But in the example 100.0, we have 4 significant figures. Why? Because there is a decimal point here. So trailing zeros are counted as a significant figures. In any measurement, the last digit is estimated. It represents uncertainty. For example, 23.4 mm. Here the digit 4 is estimated. This tells us how precise the measurement is. For addition and subtraction, the result must have the least number of decimal places among the values used. For a calculation like 12.346 plus 3.2, the answer is 15.546. But this answer is not correct. Since 3.2 has one decimal place and this is the least number of decimal place among the values, so the final answer will be 15.5. Here you learn that you have to round off always at the end of calculation, and round off at which decimal place is also depends on the calculations. Remember what I said in the starting of the video, why writing the final answer 3.876 as 3.88 may be wrong. The final answer always depends on the significant figures of the parameters used in the calculation. The final answer can be 3.9, can be 4 or 3.876, depends on the values of parameter. So you cannot say that 3.88 is a right answer. How significant figures are important in multiplication and division? In multiplication and division, the result must have the least number of significant figures among the values used. For example, if you multiply 3.456 to 12.1, the answer is 41.8176. But this is not the correct answer. Why? Because you have to take care of the significant figures here. Since 12.1 has the least number of significant figures, which is 3 significant figures, so the final answer must have 3 significant figures. And here the final answer is 41.8. Rounding off and significant figures remind us of a fundamental truth that a result can never be more precise than the data used to obtain it. Physics is not about writing more digits. It is about writing meaningful digits. In the next video, we will move one further step and discuss accuracy and precision. Two terms that sound similar but mean very different things in physics. Until then, measure carefully, calculate wisely, and keep enjoying physics.